A gas container A is in thermal equilibrium with another gas of the same mass in container B. If we denote the corresponding pressures and volumes by suffixes A and B, then which of the following statements is most likely to be true? The options given are PA equals PB, but VA doesn't equal to VB, PA not equal to PB, and VA equals VB. PA upon VA equals PB upon VB, and the last option is PA VA equals PB VB. For the first gas, for gas A, let's write the ideal gas equation. So PA VA is equals to nRTA. Since N and R are constants, so we can write TA equals or is proportional to PA into VA. Similarly, for gas B, let's write the ideal gas equation. PB VB is equals to N, here N a certain mass, and then over here, and then R times TB. Again N and R are constants, so TB is proportional to PB times VB. But since they are given that the gases are in thermal equilibrium, therefore TA should be equals to TB. So which means we can equate this and this equation. So we get P of A times V of A equals pressure of B times volume of B. Hence option D is the correct answer. In an ideal gas of density ρ, the pressure exerted at a temperature T is P. Then P is directly proportional to, the options given are ρ raised to minus 1 by 2, ρ raised to 0, and ρ raised to minus 2. So, since ideal gas condition has been specified, let's look at the ideal gas law. So PV equals nRT. This N is the number of moles, which can be written as mass of the gas upon the molecular weight. So this equation gets modified as PV equals mass upon molecular weight times RT. So just let us take pressure on one side. So mass upon the volume V into 1 upon molecular weight times RT. Now in this equation, as you can see, the molecular weight of the gas remains fixed. The universal gas constant is fixed. The temperature for the given condition is the same and it isn't changing. So basically pressure is proportional to mass upon volume. That is nothing but pressure is proportional to the density. Hence option A is the correct answer. Attractive forces and size effects in a real gas can be neglected at, the options are low pressure, high temperature, low pressure and high temperature, low temperature and high pressures. Now let's look at the concept of what an ideal gas is, or what ideal gas is. Ideal gas is nothing but it has no attractive forces among the molecules, and the molecules are themselves point masses, and they possess only kinetic energy and no potential energy. So all these conditions, when you have low pressure, the mean free path that a molecule needs to cover in order to collide with another molecule is long enough. But however, if the temperature isn't taken into consideration, we may not know what is the distance between the two molecules. Similarly, at high temperature, the molecules have very high speed and therefore they have very high kinetic energy. So here they have high kinetic energy, and here they have greater distance among them. At low pressure and high temperature, these both effects are combined. The distance is greater, as well as the kinetic energy is also greater. So which means that the molecules, when subjected to low pressures and high temperatures, have a high kinetic energy, and therefore their potential energy is almost neglected, as well as since due to low pressure their mean free path is also elongated, and hence they behave as an ideal gas. Hence option C is our right answer. The pressure of a given mass of a gas at constant temperature is P and its volume is V. Then PV versus V graph is, the options given are hyperbola, straight line parallel to volume axis, straight line parallel to PV axis, and a straight line having a slope 1. Now, the PV versus V graph is a standard graph that we need to know, PV versus V. When this graph is plotted for a given gas, so the curve comes out to be a line that is parallel to the volume axis, and hence since this is a standard curve, so the answer is straight line parallel to volume axis. Hence option B is the answer. The mean free path of molecules of a gas radius r is inversely proportional to, the options given are r cube, r square, r and root of r. Now let us look at the expression for the mean free path given by lambda, which is equals to 1 upon d square n into root of 2. So this can also be written as 1 upon 4 pi r square n into root 2. I've just missed here a pi. So as we can see, lambda over here is inversely proportional to r square. So hence option B is the correct answer. The density of air at a pressure of 10 raised to 5 Newton per meter square is 1.2 kg per meter cube. Under these conditions, the RMS velocity of air molecules in meters per second is, the options given are 500, 1000, 1500 and 3000. The expression for RMS speed of the gas molecules is given by C equals 3 times P upon rho. Now in this, substituting the values, 3 times the pressure is given as 10 raised to 5 upon rho is given as 1.2. So let's write this as 3 into 10 raised to 5 upon, let's make this as 12 and multiply another 10 over here. So what we end up with is C equals 1s are 4s are, so 1 by 4 into 10 raised to 6. So taking out the root, you get 1 by 2 into 10 raised to 3. So 10 raised to 3 is nothing but 1000. So 1000 upon 2. So that is 500. Hence option A, 500 meters per second is the correct answer. At constant pressure, the temperature of 56 gram of nitrogen is raised by 5 degrees Celsius. If the value of universal gas constant is 8.31 joule per mole Kelvin, then the work done by the gas will be, the options given are 8.31 joules, 41.5 joules, 83.1 joule and 8.15 joules. Since the pressure is constant, so the work done can be given by the formula of P delta V, or P into change in the volume. This can also be replaced by the ideal gas relation. So instead of P delta V, we can write it as N R times delta T. So N is the number of moles, that can be written as mass of the gas upon the molecular weight times R into T. So the work done comes out to be, mass of the gas is given as 56 upon the molecular weight. Since nitrogen naturally exists in the form of N2 and the atomic weight of N is 14, so N2 would be 28. So 28 times R is given as 8.31 and the temperature rise is 5 degrees. So this is nothing but 2s are, so 8.31 into 2 into 5. So it is 83.1 joules, hence option C is the correct answer. A gas at a pressure P is contained in a vessel. If the masses of all the molecules are halved and their speeds are doubled, the resultant pressure will be, the options given are P by 2, P, 2P and 4P. So the formula for the pressure exerted by a gas is given as 1 by 3 times rho C square. Now rho is nothing but mass upon volume. So therefore pressure is equals to 1 by 3 mass upon volume times C square. Now, since the volume isn't changed, so volume is a constant over here. So we can say pressure is proportional to mass and C squared. So this is the first case, and the second case, pressure, the mass is halved and the speeds are doubled. So P2 would come out to be 2 times mc square. Now mc square is nothing but P1, so P2 is proportional to 2 times P1. Hence option C, 2P is the correct answer. 4 molecules of speed 2 kilometers per second, 3 kilometers per second, 4 kilometers per second and 5 kilometers per second. The RMS speed of these molecules in kilometers per second is, the options given are root of 54 upon 4, root of 54 upon 2, 3.5 and 3 root 3. In order to find out the RMS value, CRMS, what we need to do is find out the root mean square. So that is nothing but 2 square plus 3 square plus 4 square plus 5 square divided by the number of molecules, and in this case there are only 4 molecules, so 4. So this is nothing but 4 plus 9 plus 16 plus 25 upon 4. So CRMS comes out to be root of 54 upon 4. So in order to match the options, we get 54 upon 2, taking the 4 out of the root. Hence option B is the correct answer. The temperature at which oxygen molecules have same RMS velocity as that of helium molecule at NTP is, the options given are 2184 degrees Celsius, 2184 Kelvin, 1911 Kelvin and 34.12 Kelvin. Now the formula for RMS velocity can be given as root of 3 RT upon M. So for oxygen molecules it would be root of 3 R, temperature of oxygen, upon the molecular weight of oxygen. Similarly for helium, we would get 3 times RT helium upon molecular weight of helium. So let's since the RMS speed velocities have to be equal, so let's equate these two. So root of 3 RT of oxygen upon molecular weight of oxygen is equals to root of 3 times RT of helium is equals to molecular weight of helium. So squaring both sides and cancelling these 3 RT terms, so we get T naught or T oxygen upon molecular weight of oxygen is equals to T of helium on molecular weight of helium. So the temperature of oxygen will be temperature of helium times mass of oxygen upon mass of helium. So at normal temperature and pressure, the temperature of helium we can take as 1 or 0 degrees Celsius, so that is nothing but 273 Kelvin, into molecular weight of oxygen, O2 is 32 and H2 He2 is 4. So T naught, when we solve this, we get it as 2184 Kelvin. Since 273 is in Kelvin, the temperature of oxygen, we get it as Kelvin. Hence option B is the correct answer. The temperature at which oxygen molecules will have the same RMS velocity as that of hydrogen molecules at minus 100 degrees Celsius is, the options given are 3049 degrees Celsius, 2768 degrees Celsius, 2500 degrees Celsius and 2495 degrees Celsius. The formula for RMS velocity is given as root of 3 RT upon M. So for oxygen molecules, we would replace by the suffix O. So C of oxygen, and C of hydrogen, we would simply replace 3RT of hydrogen upon molecular weight of hydrogen. So since the RMS velocities are to be equal, so therefore equating these two expressions, we get root of 3RT oxygen upon molecular weight of oxygen equals root of 3RT of hydrogen upon molecular weight of hydrogen. So cancelling these two 3R's and taking out of the root, so TO upon MO is equals to TH upon MH. So the temperature of for oxygen can be taken on one side as TH times MO upon MH. So the temperature of hydrogen is given as minus 100 degrees Celsius. So a side note here, minus 100 degrees Celsius is nothing but 273 minus 100. So it is 173 Kelvin. So 173 times molecular weight of oxygen is 32 and molecular weight of hydrogen is 2. So solving this 16, so T naught is 173 times 16. When we solve this, we get a value of 2768. But this value is in Kelvin, and we have the options in degrees Celsius. So let us subtract 273. So the value that comes up is 2495 degrees Celsius, and this matches with option D. Hence option D is the correct answer. The RMS velocity of hydrogen molecules at 300 Kelvin is 1930 meters per second. Then the RMS velocity of oxygen molecules at 1200 Kelvin will be, the options given are 482.5 meters per second, 1930 meters per second, 965 meters per second, and 3860 meters per second. So the formula for RMS velocity is root of 3RT upon M. So, and for hydrogen would be similarly 3RT of hydrogen upon molecular weight of hydrogen. So let's divide these two equations. So C naught upon CH would come out to be TO upon TH times MH upon MO. So the temperature of oxygen is given as 1200, so 1200 upon 300 Kelvin for the hydrogen. Mass of molecular weight of hydrogen is 2 and molecular weight of oxygen is 32. So solving this, we get root of 1 upon 4. So CO upon CH is 1 upon 4. So CO upon CH can be written as 1 by 2. So the RMS velocity of oxygen molecule CO is CH divided by 2. So CH is given as 1930 upon 2. So this value comes out as 965 meters per second. Hence option C, option 3 is the correct answer. At room temperature, the RMS speed of the molecules of a certain diatomic gas is found to be 1930 meters per second. The gas is, options given are H2, F2, O2 and Cl2. Now, the formula for RMS velocity is root of 3RT upon M. Here M is the molecular weight, and this molecular weight we'll need to find out in order to determine which gas it is. So squaring both sides, we get C square equals 3RT upon M. So M would be nothing but 3RT upon C square. Now 3RT, so 3 times R is given as 8.31, and the temperature is given as room temperature. Now room temperature is 27 degrees Celsius. So converting it to Kelvin, adding 273 to 27, we get 300 Kelvin. So into 300 upon C square is given as 1930 square. So when we solve this, we approximately get the value as 2 into 10 raised to minus 3 kg. That is nothing but 2 grams. And out of these options, only hydrogen is the one which has a molecular weight of 2 grams. Hence, hydrogen is the correct answer. To what temperature should hydrogen at 327 degrees Celsius be cooled at constant pressure so that the root mean square velocity of its molecules becomes half of its previous value? The options given are minus 123 degrees Celsius, 123 degrees Celsius, minus 100 degrees Celsius and 0 degrees Celsius. Now, as we know, the formula for root mean square is root of 3 RT upon M. So therefore, since in this case R and M aren't changing, so C is directly proportional to root of T. So for the second case, C2, the RMS velocity is half and of the C1. So we can write it as root of T2 upon T1. So C2 is half of C1 upon C1 is equals to root of T2 is what we need to find out, and T1 is given as 327 degrees Celsius. 327 when added to 273 to convert it into kelvins, we get as 600 kelvins. So 600. So this gets cancelled. So 1 by 4, removing the root. So that is squaring both sides. We get T2 upon 600. So T2 is nothing but 600 upon 4. So that comes out as 150 Kelvin. Now in order to convert into degrees Celsius, let's subtract this value by 273. So this we find out and it comes to be as minus 123 degrees Celsius. Hence option A is the correct answer. A gas is compressed isothermally. The RMS velocity of its molecules, options given are increases, decreases, first increases, then decreases, and the last option is remains the same. So the formula for RMS is root of 3 RT upon M, and in this C is proportional to root of T. And since C is proportional to root of T and isothermal condition is nothing but constant temperature. So since T is constant, so C2 or the changed RMS value would be constant and equal to the previous one. Hence option B, that is remains the same, is the correct answer. The amount of heat required to raise the temperature of 1 gram of helium at NTP from T1 Kelvin to T2 Kelvin is, the options given are 3 by 2 NaKb T2 minus T1, 3 by 4 NaKb T2 minus T1, 3 by 4 NaKb T2 by T1 and 3 by 8 NaKb T2 minus T1. Now the formula for the heat required is given by F upon 2 Nr delta T, where F is the degrees of freedom, and since helium is a noble gas, it's a monoatomic gas, so F for helium is 3. So 3 upon 2 Nr delta T. But however, since we can see that the options contain Avogadro's number and Boltzmann's constant, so let us modify this answer. So 3 upon 2, the N or number of moles can be written as mass upon molecular mass, and R can be, let's just multiply and divide by the Avogadro's number times delta T. So 3 upon 2, so mass is given as 1 gram and the molecular mass of helium is 4 times R upon Na can be written as Boltzmann constant, and then this Avogadro's number as it is, and delta T. So that is 3 upon 8 Kb Na, and delta T can be written as T2 minus T1. Hence, this matches option D. Hence, option D is the correct answer. The kinetic energy of 1 gram molecule of a gas at 127 degrees Celsius is, the value of universal gas constant R is given as 8.31 joule per mole Kelvin. The options are 4.986 into 10 raised to 2 joules, 49.86 into 10 raised to 2 joules, 49.86 into 10 raised to 3 joules, and 49.86 into 10 raised to 5 joules. Now the kinetic energy of a gas is given as 3 by 2 nRT. Now since we have been given 1 gram molecule, so the value of N is 1. So the kinetic energy is now modified as 3 by 2 RT. So 3 upon 2, R is given as 8.31 into T is given as 127 degrees Celsius. So 127 plus 273 in order to convert it into Kelvin. So 3 upon 2 times 8.31 into 400 Kelvin. So on solving this, we get 49.86 into 10 raised to 2 joules. Hence option B is the correct answer. At 27 degrees Celsius temperature, the kinetic energy of an ideal gas is E1. If the temperature is increased to 327 degrees Celsius, the kinetic energy will be, the options given are 2 times E1, E1 root 2 times E1, and E1 by root 2. Now the formula for kinetic energy, E is nothing but 3 upon 2 nRT. As we can see in this, since the number of moles are not changing and R is a gas constant, so E is basically proportional to the temperature. So therefore E2 for the second case upon E1 can be written as T2 upon T1. So E2 upon E1 is given as, T2 is 327 degrees Celsius, so 327 plus 273. It's important to note that we need to convert it into Kelvin, the temperatures. So plus upon 27 plus 273. So this is 600 upon this value comes out to be 300. So this is nothing but 2. So E2 is equals to twice of E1. Hence option A is the correct answer. The kinetic energy of an ideal gas per meter cube at NTP is, the options given are 1.01 into 10 raised to 3 joules per meter cube, 0.506 into 10 raised to 3 meters per joule per meter cube, 1.52 into 10 raised to 3 joule per meter cube, and 2.026 into 10 raised to 3 joules per meter cube. So the kinetic energy is given by 3 by 2 times nRT. Now from ideal gas relation, nRT can be substituted as 3 upon 2 PV. So kinetic energy is equals to 3 by 2 times PV. However, since they have asked per meter cube, so kinetic energy per meter cube, or that is volume, is 3 upon 2 times P. So 3 upon 2 times the normal temperature and pressure is atmospheric pressure, that is 1.013 into 10 raised to 5 pascals. So this value, when we solve this value, it comes out to be around 1.519 into 10 raised to 5 joules per meter cube, since per meter cube of value is asked. So this can be approximated to be, the kinetic energy can be approximated to be 1.52 into 10 raised to 5 joules per meter cube. Hence option 3 is the correct answer. Kinetic energy of gas per mole at NTP is, the value of universal gas constant is given as 8.31 joule per mole Kelvin, and the options are 3.4 into 10 raised to 3 joules per mole, 3.26 into 10 raised to 3 joules per mole, 1.7 into 10 raised to 3 joules per mole and 3.4 into 10 raised to 3 joules per mole. Now the formula for kinetic energy is nothing but 3 upon 2 nRT. Now since they've asked for per mole, so kinetic energy per mole is nothing but 3 upon 2 times RT. Now substituting the values for NTP condition of R and T, so 3 upon 2, R is given as 8.31 and the temperature, normal temperature is 0 degrees Celsius, that is nothing but 273 Kelvin. So kinetic energy per mole, when we solve this, we get the answer around 3.4 into 10 raised to 3 joules per mole. Hence, option A is the correct answer. Kinetic energy possessed by 1 gram of helium gas at NTP is, the options given are 850.7 joules, 750.7 joules, 831 joules and 663 joules. So 1 gram, so kinetic energy is given as 3 upon 2 nRT. Now this number of moles can be given as mass upon molecular weight times R into T. So kinetic energy per mass, per unit mass, is nothing but 3 upon 2 times RT upon molecular weight. So mass is given as 1 gram, so kinetic energy per unit mass or 1 gram is 3 upon 2. R is given, the standard value for R is 8.31 and the NTP value for temperature is 0 degrees Celsius, that is 273 Kelvin, and molecular weight of helium is 4. So solving this equation, we get the value of kinetic energy per unit mass for 1 gram is nothing but 850.7 joules. Hence option 1 is the correct answer. Which of the following relations is correct for the RMS speed of the molecules of a gas at temperature T? The K is given as Boltzmann's constant and M is given as the mass of the molecule. The options given are root of 3 kT upon m, root of 8 kT upon m times pi, root of 2 kT upon m, and root of m upon 3 kT. Now the RMS value or RMS speed is given by the expression C is equals to root of 3 times RT upon m. Now this is the standard relation and we need to convert it in order to get Boltzmann's constant and the mass of the molecule. So let's modify this relation. So 3R, let's multiply and divide by the Avogadro's number times T upon m. So R upon Na is nothing but the Boltzmann's constant. So therefore C is 3 times Kb Na T upon m. Now the total mass of the gas upon number of molecules per mole, or the Avogadro's number, will give us the mass of each molecule. So C would now be root of 3 Kb T upon the m upon Na can be written as small m or mass of the molecule, and this is similar to expression A. Hence option A is the correct answer. What temperature does the average translational kinetic energy for a molecule in a gas become equal to kinetic energy of an electron accelerated from rest through a potential difference of 5 volts? Boltzmann's constant is given as 1.38 into 10 raised to minus 3 joule per Kelvin. The options are 3.865 into 10 raised to 2 Kelvin, 3.865 into 10 raised to 3 Kelvin, 3.865 into 10 raised to 4 Kelvin, and 3.865 into 10 raised to 5 Kelvin. Now the kinetic energy of an electron that is accelerated through a potential difference of 5 volts can be given as EV. It is the charge on the electron and the voltage. And similarly, kinetic energy for the gas molecule is given by 3 by 2 times kT. In terms of Boltzmann's constant, it can be written as 3 by 2 times kT. So therefore, equating these two expressions, we get EV is equal to 3 by 2 times kT. So in order to find out the temperature, T is equals to 2 EV upon 3K. So substituting these standard values, to charge on the electron is 1.6 into 10 raised to minus 19 and 5 volts upon 3 times the value of Boltzmann's constant is given as 1.38 into 10 raised to minus 23. So this expression gives us the value of T as 3.865 into 10 raised to 2 Kelvin. Hence option A is the correct answer. A cylinder of capacity 20 liter is filled with hydrogen gas. The total average kinetic energy of translatory motion of its molecules is 1.5 into 10 raised to 5 joules. The pressure of hydrogen in the cylinder is, the options given are 2 into 10 raised to 6 newtons per meter, 3 into 10 raised to 6 newtons per meter square, 4 into 10 raised to 6 newton per meter square, and 5 into 10 raised to 6 newton per meter square. Now, the average kinetic energy is given by the relation 3 by 2 times nRT. Now, from the ideal gas relation, nRT can be written as 3 upon 2 times PV. Now, so therefore, the kinetic energy is given as 1.5 into 10 raised to 5 joules is equals to 3 upon 2 times pressure into volume is given as 20 liters. So 20 liters is nothing but 20 into 10 raised to minus 3 meter cube. So solving this relation in order to find out the value of P, we get the value of P as 1.5 into 10 raised to 5 times 2 upon 3 into 20 into 10 raised to minus 3. So solving this, we get the value of this expression as 5 into 10 raised to 6 newtons per meter square. Hence option number 4 is the correct answer. Two gases are at absolute temperatures 300 Kelvin and 360 Kelvin respectively. The ratio of average kinetic energies of their molecules is, the options given are root of 3.5 upon 3, 2 is to 7, root of 3 upon 3.5 and 36 is to 49. Pardon me, this is 6 is to 7. So as we know, kinetic energy is, or the absolute energy, kinetic energy is nothing but 3 upon 2 nRT, and from this we can conclude that energy is proportional to T. So therefore, for the two conditions, E1 upon E2 is T1 upon T2. Now the temperatures are given as 300 upon 350. So this ratio comes out as 6 is to 7. So therefore E1 and E2 are in the ratio of 6 is to 7. Hence option B is the correct answer. What is the value of R by Cp for a diatomic gas? The options given are 3 by 4, 3 by 5, 2 by 7 and 5 by 7. Now Cp for a general gas is given as 1 plus F by 2 times R, where F is nothing but the degree of freedom. Now for a diatomic gas, the degree of freedom F is 5. Therefore the value of Cp is 1 plus 5 by 2 times R. So Cp is equals to 7 by 2 R. So R upon Cp is nothing but 2 upon 7. Hence option C is the correct answer. For a gas, R upon Cv is equals to 0.67. This gas is made up of molecules which are, the options given are diatomic, mixture of diatomic and polyatomic, monoatomic and polyatomic. Now, as we know, the general expression for Cv is equals to half F into R, where F is nothing but the degree of freedom. We need to find out the degree of freedom of the gas so that we can determine the nature of the gas. So therefore, Cv upon R is equals to 1 by 2 times F. So F So therefore Cv upon R is 1 upon 0.67 is equals to 1 by 2 times F. So F is equals to 2 upon 0.67. The value of 2 upon 0.67 is very close to 3, and the degree of freedom is 3 for monoatomic gases. So therefore, option number 3, monoatomic gas, is the correct answer. For an ideal gas of diatomic molecules, the expressions given are Cp is equals to 5 by 2R, Cv is equals to 3 by 2R, Cp minus Cv is equals to 2R, and Cp is equals to 7 by 2R. Let's look at both the expressions for Cp and Cv. First, let's look at Cv. Cv is equals to, for a general gas, is 1 by 2 F into R. Now, F, or the degree of freedom for diatomic gases, is 5 for diatomic gases. So, 5 upon 2R. So, this is the value of Cv, and since there is no option which matches, let's look at Cp. Cp, the general relation is 1 plus F by 2 times R. Again putting F as 5 for diatomic, so therefore 1 plus 5 by 2 times R, we get it as 7 by 2 R. Option D matches the similar relation, and therefore option number 4 is the correct answer. A diatomic gas molecule has translational, rotational and vibrational degrees of freedom. The Cp upon Cv is, the options given are 1.29, 1.33, 1.40 and 1.67. Now let's find out the degrees of freedom F. Since it has translational, so translation has 3 degrees of freedom, rotational adds to 2 degrees, and there's 1 vibratory motion, so that is 1. So total degrees of freedom is 3 plus 2 plus 1, that is 6. Now 6 degrees of freedom, Cp is given as 1 plus F by 2 times R, and Cv is 1 upon 2 times F into R. So therefore Cp upon Cv we get as 1 plus F by 2 R upon half of F into R. So R gets cancelled. This relation comes as 2 plus F upon F. So that is nothing but 1 plus 2 upon F. Cp upon Cv. Now substituting the value of F as 6, we get 1 plus 2 upon 6, that is 1 plus 1 by 3. So 1 plus 1 by 3 is 1 plus 1 by 3, 0.33. So that is 1.33. Hence option number B is the correct answer. During an adiabatic process, the pressure of a gas is found to be proportional to the cube of its temperature. The ratio of Cp upon Cv for the gas is, the options are 2, 5 by 3, 3 by 2 and 4 by 3. Now, the given condition is that the pressure is proportional to the cube of the temperature, and the ideal gas relation gives PV equals nRT. So your T is proportional to PV. So instead of T, we can write P is proportional to PV cube. So taking it on this side, so P square V cube is equals to a constant. Now let's write this in a modified form or taking the square root. So p v raised to 3 by 2 is equals to again a constant. Now this is in the general form, pv raised to gamma is equals to constant, and this is a indication of an adiabatic process. And in this, the value of gamma is nothing but Cp upon Cv. So therefore, if this is Pv raised to gamma, which is a constant, so gamma should be 3 by 2. So gamma is 3 by 2, and which implies that Cp upon Cv is also 3 by 2. Hence option C is the correct answer.